Good morning. Yes, midterm is on Wednesday. A calculator is allowed. You are also allowed a one-page. You are allowed 1 page of notes, double-sided. So please prepare that. It will help you tremendously if you write out a bunch of notes ahead of time. Probably won't even use the sheet, but it will just be helpful to help you, just prepare and think through all the different topics that we've talked about. Question.
How big could it should be?
8.5 by 11, normal letter size. What was that? One page, double-sided. Yeah. On the final, you are allowed a second page. So you're welcome to use the 8.5 by 11 that you wrote right for this midterm, and you're welcome to use that again for your final, because you're allowed 2 pages on the final. Yeah, okay. So a lot of people asked some really good questions in the midterm review Piazza post that I made. And I think probably first is I want to go over some homework 3 questions. I think that will probably be helpful. Someone was asking for question 4. I think this is a good question to start on. Okay, so first question. What is the clock to Q delay of this? What is this? 1, right? It's just clock signal right here to Q, just 1 nanosecond. Okay, done. 1 nanosecond. Next, assume 2 nanosecond setup time, 5 nanosecond hold time. Okay, hold on. So what I like to do whenever I'm looking at setup time, hold time, is I want to draw out the timing aperture. So at what time step does the timing aperture start at? Sure, 1, and then where does it end? 8, I think. 5, so 1, 2, 3, 4, 5, yep. So this whole length right here, that is the time in which D must be steady for. And if D changes in the middle of that, it means either setup or a hold time violation. We need to look at the expected Q. Okay, so in this case, do we have a setup or hold time violation? Yeah, hold time. Why do we have a hold time violation? Well, because we were expecting it to be 1 on the output. Like we were expecting it to be 1, but it did not stay at 1 this whole time. In fact, it dropped to 0 right at the end. Yeah. Side tangent. What if the expected Q instead of this was actually maybe something like that, where it started at 1 and then dropped down? Okay, if this was our expected Q, so it's now like inverted, then would this now be a setup violation or a hold violation? Yeah, we would call this a setup violation because we were expecting it to, honestly, I feel like maybe this doesn't make the most amount of sense because the hold time is so much longer than the clock to Q. But I guess the example still stands of like the expected Q is what you look at to determine whether it's a setup violation or hold violation because we're expecting it to drop to 0, but it did not it wasn't 0 until like at the very end. So therefore, it wasn't like set up at 0 early enough. So therefore, this would be a setup violation. Question.
I just had a quick question on why it would be a setup violation because I was under the impression that setup violation was happening in the first 2 nanoseconds.
Yes. So I'm saying, so if we expected, am I saying this wrong? Yes, right. So we're expecting it to drop to 0 here, but D is set to 1. And it's set to 1 until finally it ends up turning to 0 correctly, but it happens way too late. It happens like 6 nanoseconds too late, or however long that is, Because we were expecting it to be 0, and it finally reached 0, but after like a long delay. But if we go with the actual, so I'm just saying like if, for this green case, it would be a setup violation. But for this black one, it would be a hold violation. So the actual, whatever. So this question is saying it does have a hold violation, but then it's asking now, how do we fix the hold time violation? Question.
I'm not convinced
Right, so we know that there is a violation because D changes in the middle of the timing aperture. So we know that a violation happens, but then we need to look to Q to figure out what type of violation occurred. Because if we looked at Q and we were expecting it to jump to 1, then we would know it's a hold time violation because it wasn't held at 1 the entire time. But if we wanted it to go down to 0, then we would know this is a setup violation because it was not set up at 0 early enough for the whole time. So basically, you can just look at whatever the expected output is, and it's like, does the expected output equal what D is like held for the entire length of the timing aperture? If D is 1, if D like starts at 1, but you were expecting it to start at 0, then that would be a setup time violation. If it started correctly, so if it started like, yeah, here we can see it expects 1. If it now is set up at 1, so this is now good, but then it changes too early, then that's a hold time violation. Yeah, okay, I'm gonna move on from that. But okay, so just kind of, this is given to you, though, that this will create a hold time violation in this case. And then now the question is, well, how much additional combinational delay should be added before D to prevent hold time violations? So in other words, so we have this D right here. The question is, how much do we have to shift it over by? Like, how much additional delay do we have to add to it in order to make this now no longer have a timing violation? Yeah, right, just one single step right here. Because if we shift it by just one single step, then we're good. We have no more timing violation. Yeah. So therefore, right here, this would be 1 nanosecond combinational delay. Okay. Okay, so now for C, so it says, okay, assuming this waveform, D is driven by combinational logic fed from another flip-flop with the same clock and the same clock to Q as the flip-flop shown. What is the delay of the combinational logic driving D as depicted in this waveform? Okay, a little bit complicated, but it's way easier to think about this if we draw a schematic. So it's saying, okay, so D is driven by combinational logic. So if we will have a flip-flop, so D, Q, clock. And so D is driven by combinational logic. So maybe it's just an inverter or something. I don't know, black box combinational logic. Right. But this combinational logic is from another flip-flop. So we have this structure right here. So we have a flip-flop that drives combinational logic into another flip-flop. And this flip-flop is kind of like implied, right? This is the flip-flop that's actually shown in the diagram here. And so we're saying that assume that this D right here, assume that this D is this D, and it's saying like, well, how long is this combinational delay? Okay, well, what we can do is we can look at these signals up here. So what is the clock to Q again? Yeah, so the clock to Q is just 1 nanosecond. So we know that, like, starting out, I'm gonna. So this is, the clock to Q is 1 nanosecond. So starting out, so it takes 1 nanosecond for it to leave the flip-flop. And then after that, then it's some unknown delay, and then we see what the value is. So here we see what the value is, so therefore this delay right here in the middle is probably going to be this length. What is this length? Yeah, 3 nanoseconds. So therefore, this combinational delay has 3 nanoseconds of delay. Is that how we solved it? This makes sense. Yeah. Also, in a circuit, just in the world, every single path of combinational logic, like all combinational logic, in every single case, will come out of a flip-flop and will go into another flip-flop. Like that is all that combinational logic is. It's kind of just like a driver from one flip-flop into another flip-flop. Granted, I mean, you could maybe have it come out of like a RAM instead. So maybe it's like out of a RAM into combinational logic into a flip-flop, or it can be out of flip-flop into combinational logic into a RAM. But you're always going to have some sort of clocked device feeding it through combinational logic and then back into another clocked device. So yeah, so just whenever you have questions like, oh, like what is the delay here, you should always assume that it's maybe like coming out of another flip-flop, implicit, kind of like this. Yeah, question?
So for 4C, we're not really caring about hold time or setup time?
Yeah, I don't think you have to, right. Yes, correct. So in this case, yeah, you don't have to care about hold time or setup time. You do have to care about this clock to queue. So, okay, so this was 3 nanoseconds. All right, great. So now it says assume for 4D, so assume 2 nanosecond setup time, assume -1 nanosecond hold time. So where does the timing aperture start for this? 1? Yeah, where does it end? 2. Yeah, because we have a -1 nanosecond hold time. So therefore it will be 1 nanosecond before the pause edge. So this is our timing aperture for this question. Okay. Also assume the maximum delay of the combinational logic driving D is the same value as what was calculated in part C. Okay, so the combinational logic is going to be 3 nanoseconds. Then it asks what is the minimum clock period of the circuit without creating timing violations. So therefore, we have our setup time, hold time, and clock to queue, and combinational delay figured out. So how do we calculate now our minimum clock period? What do we add up? What's the first thing? Yeah.
Setup time?
Yeah. I would say conceptually, it's probably best to add setup time last, because that's kind of the last thing that you think about, because the setup time is like after it comes out of the flip-flop, goes through, finally, at the end, it adds up setup time. So I would not probably add setup time first. Yeah, what should we add first? Yeah, so first it's clock to queue, so that'll be 1 nanosecond. I'll do it in blue again. 1 nanosecond, and then plus, what's the next thing it goes through? Yep, so that is 3 nanoseconds, and then what is the final thing? Yeah, and then finally it is setup time, so that will be 2 nanoseconds. So in total, the clock period will be what? Yeah, so 6. Right. Could we have a clock that had a longer period and still did not cause timing violations? I think so, yeah. Could we have a clock with a shorter clock period and not have timing violations? Yeah, we could not. Right. Okay. Cool. Okay. So if we have a 6 nanosecond. Oh yeah, question.
I just have a question about like the negative hold time.
Yeah.
If there's a negative hold time, what counts as like a hold time violation?
Mm-hmm.
Isn't it never gonna like?
In this class, I will not talk about clock skews, but there's an idea that actually all your flip-flops, even though they're connected to the same clock wire, they actually will still operate at slightly different times depending on like how far away flip-flops are from one another or how far away like the clock wire is. So because of that, not all the flip-flops fire at exactly the same time. There's something called clock skew. In this class, you can assume, maybe you should write this down. In this class, you can assume that when you have negative hold time, you will never have a hold time violation. So if I ever say like, oh, like assume negative hold time, you should go, whew, okay, like the question's going to be easier. I don't need to think about hold time. Yeah, negative hold time is your friend in this class. If you're learning about like clock skew, then you have to factor it in and think about that. Yes? Right, it does not affect the, so the hold time does not affect the clock frequency, clock period at all, regardless of if it's positive or negative. And that's because like it's just, the hold time is just saying like basically how long is the combinational delay. Like it's more related to the combinational delay. It's just like if you had to hold it for a longer amount of time, then it doesn't really have anything to do with the clock period, because like the most important thing is just satisfying this setup time and then making sure that the signals are held for long enough from like the previous cycle. Yeah, so it's not factored in. Question.
I had a question about like the negative hold time. I think I did it wrong, but the way I like set up the diagram for that was that there's like -2 for like from behind the blockage it's 2 nanoseconds of cycle time, and then the negative hold time overlaps with that, like also starting at the positive blockage, so that the time capture is 2 seconds.
I see.
Like, does that not?
Correct, yeah, so-
Over now, it's like shifted, so it's not actually like hitting the clock edge anymore.
Right, exactly, yeah. So in this case, you can see that even though like we're saying like, oh, make sure your signal is set up, whatever, 2 nanoseconds before the clock edge, we actually don't need to hold it all the way until the clock edge. Like it's okay, like we can still pass setup time, even if like we were to have our value change. Like if D now changed like right here before the clock edge, that still is okay. That still does not create like a setup violation. Yeah. Was that your question?
Yeah, so the timing after is 1 nanosecond.
Yes, right. If the only thing that denotes whether we have a timing violation is if we change anywhere within this region. If D changes in this region, then we have a violation. If it's outside this region, then we're good. Yeah, question.
So just to confirm, if we had a positive hold time,
Uh-huh.
we would be adding that to our calculation for D, right?
No, for the clock period, you're saying?
Yes.
No. Yeah, for hold time, you never factor in hold time. The hold time is just whether or not your circuit works. It's not necessarily how fast your circuit can run at. Yeah. Yeah. Okay. Cool. 6 nanoseconds is our minimum clock period. What is that converted to clock frequency? Does everyone have their calculator on them? So 1 divided by 6 nanoseconds. Yeah.
Well, it's about 167.
Yeah, right. So this is about 167 megahertz is the maximum clock frequency that we can run at. Okay, so in this case, so assume now we are running at 100 megahertz, very reasonable clock frequency. Does the circuit experience a setup time violation, hold time violation, or no violation? Okay, well, remember, so our hold time is -1 nanoseconds. So therefore, in this question, it is impossible for us to have a hold time violation. So we can cross that off. That's not the problem. And also, we calculated that. So that is the maximum allowed clock frequency to not have any timing violations. So therefore, I believe that this should have no violation because 100 megahertz is less than 167 megahertz. So this is no violation. Yeah. And then finally, though, for this 200 megahertz, what timing violation will this create? Yeah, this will create a setup time violation. Because now our clock is running too fast, so the D's, like the combinational logic, isn't able to propagate fast enough. It isn't able to arrive fast enough to set up for the next cycle if we're running this fast. Yeah. Okay. Yeah.
So is running too fast always going to be a setup time violation?
Yes. Yeah.
Sorry, I think you already explained this, but can you just quickly explain again why the -1 second hold time in part D is like positive when you add them up there?
So I'm not adding the hold time at all in the clock period. And when you calculate the clock period, you should not add hold time. You only add setup time.
Oh, okay.
Yeah.
What's the 1 nanosecond then there?
That is clock to queue.
Oh, okay, I see.
Yeah. Yeah, question.
The reason why setup time violation isn't because it's affecting the next cycle setup.
Exactly. Yeah. Right. I mean, the clock frequency is too fast, so the flip-flop is sampling, it's sampling, but there isn't enough time in between the samples for the previous cycle's combinational delay to propagate through all of the circuit and then arrive at the flip-flop like early enough to satisfy setup time. Yeah. Yeah. Question. Yeah.
So if the setup time is 2 nanoseconds and the hold time is -1,
Yes.
and then D changed in between 2 and 3 nanoseconds, that
Yes.
would be a setup time violation.
Correct. That would be totally allowed if D changes in this region.
So whatever negative hold time is away from the setup time.
Yeah, you can think of it that way. Yeah. Yeah. Question. Oh.
Is it possible for like the clock to be too slow and it like causes like a hold time violation?
No, that will not cause any problems. Yeah. I will leave that for you to figure out. Yeah, question.
Okay, yeah, wait, so to clarify, so basically the meta clock here, so that term is the maximum frequency, yes?
Yes, exactly. Yeah. Right. Yeah,
Is
question.
there a special name for like a violation if your combinational logic takes too long?
Setup violation. If your combinational takes too long, then that would be a setup violation. Yeah. Yeah. Was there something else you? Okay. Okay. Cool. Yeah. Well, here are all the answers on this question. So, go home and really study all these and be like, like how do I really understand this for when I'm asked a very similar question on the midterm on Wednesday. Yeah, this was actually, I will say that this question was exactly like word for word pulled out of last quarter's final. So there will be a very similar question to this. I think it's a really good kind of conceptual thing to understand everything. Yeah, question.
This is just a quick one, but for question 2, we're asked to do a waveform of a multi-bit number.
Yes.
How would you like this to represent?
Yeah, great question. So same way as like GTK wave, where like if maybe like on this cycle right here, maybe Q stored the value of 6, you would just write 6. And maybe on the next cycle, maybe it stored the value of, on the next cycle, maybe it stored the value of 9 or something, then you would just write in 9. Oh, let's say 2 instead. There we go. Yeah. Okay. Yeah, you can just write in the number like this. And maybe just to like make it extra clear, you could just write like little lines right here to separate out each clock cycle. Okay. Cool. So there were other questions. I want to get through the Piazza questions because I like them. 5B? Yeah, 5. Okay, this is good. So I don't think we'll go through all of these, but okay, this first one right here. So 0, 0 says the operation is no change. So how do we implement this? So right here, this 0, 0, what do we put for this input? For, to make sure that we have the no change operation implemented. What do we do for this?
Goes into Q.
Yeah, right. So just you can take this Q directly and just do that, right? That's what you're thinking. Yeah, and so we can do that probably for all of these. So we can just take each one of these and just feed it back into 0, feed back into 0. Right? Okay. Similarly, let's try the left shift now. So left shift is this input right there. So how do we feed this now and make it work? Yeah, so so to left shift it. So I guess I'm backwards. I keep like mentioning like the wrong direction, so I apologize for that. Yeah, so what you do is you take whatever is on the left, whatever's stored in the left, whatever's stored on the right, and then you bring it over into the left. So yeah, so what you do is you take this Q right here, take it out, and then feed it in like that. And then similarly, now for this one, that, and then this last one, that. And then we're missing, now this input, what should this 1 be? So it's not 0. What is it? SI, yeah. What does SI mean? Serial in, yeah. So SI goes in right here. There we go. Okay. So that's the first half of that question done. I won't spoil the rest of it. But yeah, I mean, as you go through this question, what you will see is that every single flip-flop, like every single path that you get through this, is a single flip-flop and then being outputted through a mux into another flip-flop. That's all that you have. You never have a case where it's like out of one flip-flop and then through like 3 muxes and then through like an adder or something. Like it only goes through one flip-flop, through one mux, into another flip-flop. Like that is the longest path that this will ever have. So in that case, then let's find the maximum clock frequency. Okay. What is the first thing that? Question. Yeah.
Yeah. What is load? And what's like the load?
Oh, so load is just another input. So we can just say like, we can just directly like for this x3d, we can directly just write in load 3 next to that input.
Oh, that's like the input for the load.
Yeah, right. Yeah. You can just assume that all of these symbols right here are inputs into the system. Yeah. Maybe I should have denoted that. That's good. That's a good point. Okay. Okay, cool. What is the first thing that we add to figure out clock period? Clock to Q. Okay, what is clock to Q? In this question, what is the clock to Q? Yeah, 150. What is the combinational delay? Yep, 300 picoseconds, because it is just one single mux. It will never go through more than one mux, so it'll always be 300 picoseconds. And then finally, what's the last delay that we add? Yep, setup time, and that is 200. Okay. Also, we have a hold time of negative 50 picoseconds. So, do we have a hold time violation? No. How do we know it's how do we know it's not a hold time violation? It's negative. Yeah. If it's negative, you can just be like, great. Okay, throw it away. Don't think about it. Let's say the hold time violation was, let's say that the hold time was maybe 500 picoseconds. Then would we have a hold time violation in that case? If hold time was 500 picoseconds?
No.
I think so, yeah. If it was positive 500, then in that case, the clock to Q plus the mux delay, this would be still less than 500, so therefore we would have a hold time violation. In that case, how would we fix this? More combinational delay, yeah. So you would add some buffers. I will also note that buffers are added by your tool automatically. So it's not something that you have to do in Verilog. Like if you you will generally never experience a hold time violation when writing Verilog because your tool will go through a lot of work to make sure it's all good for you automatically. Sometimes you can have a hold time violation, but I won't get into that. Most of the time, though, the tool automatically inserts buffers for you if it expects that there's a hold time violation. Yeah, question.
Is it negative hold time? Like, is that just theoretical for these questions, or would that actually?
Oh, actually, so most flip-flops have negative hold time in the real world, yeah. Including the Sky 130 PDK that I keep referencing, the open source PDK. All those flip-flops have negative hold time. Yeah. Yeah. Question?
Saying that there would be hold time because the 500 is less than the 150 plus 300 plus 200, or the other way around?
Oh, I'm saying that there would be a hold time violation because 500 is less than 150 plus 300. Yeah. Okay, but let's stop playing with theoreticals. Let's look at what the actual question is saying. Okay, so this now full delay. What is this added up? Yeah, I think this is 650 picoseconds. Okay, and then what is that now converted to maximum clock frequency? So this is, 1.54 megahertz? Gigahertz. Because now we're dealing with picoseconds. Okay. Cool. Now, let's assume that we have a bunch more registers. So 512 all now. Okay. Is this going to change? I think it's exactly the same, right? Because no matter what, the longest path will still just be out of one flip-flop, into a mux, into another flip-flop. And so the total possible delay from one start point to one end point in combinational path is still going to be this delay. So even if we add a bunch more registers, we will never have a longer delay anywhere. So for both of these cases, this is the clock period and clock frequency. Okay. Yeah, question.
For the incident, you should know the relationship to picosecond.
Yes, you should. Okay, cool. This was 5. Question. Trying to see what I can do kind of in parallel. Okay. This is good. So I want to quickly kind of go through question 6 now. I won't go through all of it, but someone had a really good point that I actually did not provide super good wording. Oh, you know what? It wasn't this question. It was this question. So for question 7, so this pipeline question, inside of this, I have this wording, where is it? Right here. So this question, what is the total delay after clock edge until the input to the next flip-flop is valid? I would like to kind of change this question. I think I probably just won't create this, but what I was trying to ask was, what is the minimum clock period? So that's what this question was supposed to be saying. So I responded to a Piot's post about this. I'll change it in future quarters, but yeah, it's a little bit kind of poorly worded because it's ambiguous whether you include setup or not. In this case, I'm expecting you to include the setup delay in your analysis. Yeah, okay. Yeah, question.
Sorry, can you repeat what the question actually is?
The question is, what is the minimum clock period? Okay. Yes, so register file question. So in this question, so you have, so I think it says that we assume that all of these inputs are coming out of magical flip-flops, which have 0 delay. So it comes out, whatever, into all these three. And so these have 0 clock to Q, 0 setup time, 0, whatever, 0 delay. And then, and also this as well. Q, D, okay. And then after that, then it is fed into more magical flip-flops with the 0 delay. Okay. And so now the question is, what is the maximum clock frequency that this design can run at? That's effectively what this is asking. Trying to quickly find the question again. Yeah, so question E on this is telling you to find an equation, like a piecewise equation for the clock frequency or clock period, given that the number of registers is some parameter that you can change. So it's saying like if you have like a register file with 64 elements, then what will be the clock period on that? Or if it now has like 512 elements, then what is the clock period on that? Also, like I believe it says that it stores words. What is a word? It's a little bit ambiguous. It also depends on the context. A word in computer science generally means 32 bits. So just a word is 32 bits. In this case, a word is just how many flip-flops you have stacked up. So in this case, a single word, in this case, would be 4 bits because we have 4 flip-flops all stacked up on one another. So that is what a word is in the context of digital design, like schematics like this. A word is just how many flip-flops you have stacked up. Or at least the word length. That makes sense. Yeah, question.
Wait, do you mean 4 like the size of the bus or 4 like the number of the registers?
Oh, I mean the size of the bus. There are 4 flip-flops all stacked up vertically. And I guess, yeah, unfortunately there are 4 separate words here. So each one of these like z-axis like arrays of registers, each one of these has it stores a word. And so this will be word 0, this will be word 1, this will be word 2, this will be word 3. And each word is 4 bits because it drives this 4-bit bus. Yeah. If we had now like an 8-bit word, then what would change is now all of these would change from 4 to 8, and each one of these registers would now have 8 flip-flops all stacked up on one another. This would be 8-bit words. Okay. Did anyone create piecewise function for this? Is anyone feeling confident? Yeah. Cool, yeah. We can go over it if you want, but I guess I'd rather answer other questions first because there's only 20 minutes left of class. Yeah, question.
Wait, so the registers in the middle, they belong to read frequency.
Say that again?
The registers in the middle,
Uh-huh.
they belong to the read time period.
Yeah, so right, so the read delay is just everything that happens after these flip-flops, but the write delay is everything that happens before these flip-flops. So the write delay, we can assume, yeah, is whatever comes out of this, through these decoders, and then into, like, plus then the setup time for each of these, because it's going into the D side. And then on this side, we don't care about setup time at all, because it's just the Q has, whatever, it's just the clock to Q, then it's through this mux, and then it's through this magical flip-flop with 0 delay. So it's just basically the clock to Q is all you have to worry about on this side.
What about hold time?
Sure. Does it mention what hold time is? I don't think this question, 100 picoseconds of hold time. Yeah, sure. So another way that you can tell that you will not have a hold time violation is anytime that your hold time is less than your clock to Q. So in this case, your clock to Q is so slow that by the time it finally produces a result, we already had held our flip-flop valid for that amount of time. So anytime that we have a hold time that is less than clock to Q, then we're also good, and we don't need to worry about hold time. So in this case, yeah, we don't have a hold time violation. I hope you're all like frantically writing this down. I'm giving you lots of good like rules of thumbs to be like, oh, like, okay, like sanity checks on things. Okay. So I've kind of touched on most of the Piazza questions. Does anyone want me to go in depth on anything else, or do you have any other questions and things? Yes, question.
For 5B,
Yeah.
for the 512 word shift, do we also multiply it with the setup as well, or is that after we add the delay and then clock to Q and mux? Then I will multiply the 512 and then add the.
So it's asking for the maximum clock frequency, and in both the 4 word shift register and the 512 word shift register, in both of these cases, this is what our clock delay and clock frequency is. So in both of these, no matter how many words there are in our shift register, we will always have this delay. So we don't need to multiply it by 512, don't need to multiply it by 4. This is just always the answer in a shift register. Yeah. Yeah, you know what, a lot of people were asking about just like when you have like a bunch of flip-flops on a line. So something like that, sure. Okay, so let's say this AND gate is like 4 nanoseconds, and then it goes into another flip-flop, and then maybe this has some input that's fed from something else, and then this now comes in and has maybe an OR gate. Maybe this is a 3-input OR gate or something, and so this runs at, I don't know, 8 nanoseconds. And then finally, maybe at the very end, there's something like really fast that happens. It's just a single inverter. Maybe this is 1 nanosecond. Comes out, goes into another flip-flop. Okay. So in this case, and let's assume clock to Q of 1 nanosecond and a setup of 1 nanosecond and hold time of -1 nanosecond. Okay. In this case then, so we have a delay that's 4 nanoseconds, delay that's 8 nanoseconds, delay that's 1 nanoseconds. What will the clock frequency be now? Or what will the clock period be, the minimum clock period, in order to make sure there's no violations through this? What is the clock period? 10, yeah, because what you do is you look at whatever the longest thing is. So in this case, like if we're just looking at this part of the circuit, what would the clock period be? 6, yeah, okay. But then if we look now at this part, then now this is 10. And since 10, like it's the minimum clock period, but it's like, okay, so now we bounded our clock period to be a little bit higher, because if we had it less than 10, then now we would have a violation on this stage. So, okay, so this is going to be like, yeah, a delay of 10. But now if we look over here, then this, if we just had this part, then it would be a delay of 3 nanoseconds. But 3 nanoseconds is faster, like it's less than 10. So 10, since this is our worst delay, then in this case, our entire design must run at 10 nanoseconds. The entire clock frequency must be 10 nanoseconds. All right, yeah, question.
Sorry, where are you getting the 2 from again? Is it just clock to Q plus setup? Or?
Exactly, yeah, thank you. Yeah, so clock to Q plus setup is 2 nanoseconds, so we add 2 to each one of these, and that is how we calculate the minimum clock period. Yeah. Okay, so that means, so if every single one of these stages now runs at a clock period of 10 nanoseconds, then actually how long will it take for data that's over here? How long will it take for forward data that's over here to propagate all the way over to this side? So let's say time equals 0. We get a pause edge here. So now we propagate through here. So 4 nanoseconds, boom, we arrive here. But then how much longer do we have to wait? Yeah, well, we have to wait for the whole clock period. So now we have to wait until basically 10 nanoseconds. So at this point, at this point, now we need to wait until 10 nanoseconds. And then boom, okay, 10 nanoseconds, this is great. Now we come out of this flip-flop, we've successfully propagated, and we get here, and then we get there just in the nick of time, perfect, and then boom, now another 10 nanoseconds, and then we come out of here, and we arrive super early, because this is just a 1 nanosecond delay. But then finally after that, then it is 30 nanoseconds before finally over here, we end up producing our result. So it takes 30 whole nanoseconds for the entire system to run its course and for the data to propagate from this stage to this, to this, to this, to this. So it takes 30 whole nanoseconds to get all the way through. But our clock frequency is still pretty fast. Our clock frequency is now it's 100 megahertz if nanoseconds is if it's 10 nanosecond clock period. So that is the whole idea with pipelining, is that if we got rid of each of these flip-flops right here, come on. So if we had gotten rid of each of these, then now our clock period would be slower, but our latency to produce a result at the end would end up being faster, because now there's less waiting that happens up here. Let's kind of just really cement that in. What would be? So remind me. So what is the maximum clock period that minimum clock period that this can run at? So this is 10. What is the minimum clock period that this design could run at? So it'd be 9 plus 8, so 12, then 13, so 13, but then plus clock to queue and plus setup. So that would be what? Yeah, so this whole delay right here would be 15 nanoseconds. And what is 15 nanoseconds converted to clock frequency? Yeah, so this would be about 67 megahertz. Versus what would 10 nanoseconds be converted to clock frequency? What would it be? 100 megahertz. Yeah. So therefore, we have a higher clock frequency here, even though this design ends up spitting out the result just a little bit faster overall. So how long would it take actually for, let's assume our clock frequency was running at the maximum speed. Then what would the time be in order for the delay, for data coming in right here to now be valid right here? How long would it take for that to happen? Yeah, so I think it'd be, so it'd be 15, but then I guess we would also probably account for the clock to queue. So maybe right here, we could say that this takes 16 nanoseconds for the data to actually propagate all the way through. Which if you remember over here, it was, for 31 nanoseconds or something to propagate all the way through. So it's almost even though clock frequency is running a little bit faster, actually, the latency is almost double. So this was 10 nanoseconds, 20 nanoseconds, and then 30 nanoseconds. So then this would be 31 nanoseconds for the data to start right here and then finally arrive all the way over here. So yeah, quite a big discrepancy. People following this? Yeah. This is a really good kind of visual example to show that, yeah, like the slowest stage, that is what sets your clock frequency for the entire rest of your design. So even though maybe your latency is worse, your clock frequency is higher. And what's important with that is, yeah, like what if something else in your design really needed to run at 100 megahertz, like it really needed this, then unfortunately you just kind of have to take this latency hit because you need to be running at a higher clock frequency. Yeah, question?
If you want your computer to run faster, wouldn't it make sense to have like less latency?
Well, kind of a nice thing though is that, so if you remember on the pipelining question in the homework, there's actually a question about throughput. So what's nice is when if you have this clock frequency of 67 megahertz, that means that the fastest that you can feed in data and the fastest you can receive data is only at 67 megahertz. But up here, the fastest that you can feed in data is actually 50% higher. It's at 100 megahertz. Like I can feed in data faster and I can receive data faster. So actually your computer ends up running faster even though the latency is longer, and that's just because like if you think of like an assembly line, it's like how quickly can you get things on and off the assembly line, not necessarily how long does it take for one single individual product to move through the assembly line and complete its course. It's more of just like how quickly can they, like at what rate, like at what throughput can things come out. Yeah, great question. Okay. Trying to think. I think we have just enough time that I want to cover. Where is it? Yeah, I think this is a good question. Did this question make sense to everyone? Yeah, question?
For part D, should we have a different sum of products equation for each output?
Exactly, yeah. So Y2, Y1, Y0, these are all three different outputs, so you will need three different sum of products for each one of these. Yeah. Okay. Yeah, I want to go over this one. I think drawing schematics is a really good kind of practice, so let me just show you how to do this. So it says design a counter. It counts up from 0 to 4. So when you think counter, so what are the two kind of units that we need? What are the two modules that we need? So with counter, what do we need? How do we draw a counter? Yeah?
An adder and a flip-flop.
Adder and a flip-flop, cool. So we have a flip-flop, and we can draw it like this. So then on the D side, this comes out, probably goes into an adder. And let's assume that it just always counts up. Then we'll probably have this sort of structure where every cycle we will add 1. So we're starting out and then goes through, adds 1, and then boom, goes through, adds 1, boom, goes through, adds 1. Sorry. Cool, okay, so this would be a normal counter. But what this is asking is it's saying when the counter equals 4, so in other words, when this part right here equals 4, so maybe we can have like an equals 4 unit that maybe we design from up here, where, I mean, this is equals whatever that number is, but maybe we have something similar that's like equals 4. And then maybe we can take this and we can feed this somehow back into here. So what do we put here? How do we use this signal? Yeah?
You put a mux.
Yeah, fantastic. Okay, so what should the mux look like? So it should take in Equals 4 is the select. And then what would the 0 case be?
0.
The other.
Yeah, I think if we are not equals to 4, then in that case we should just keep counting up like normal. But then when we are equal to 4, so when this is 1, then what happens? Yeah, we could just say 4. We could also, if we wanted, we could like take this output right here or something, feed this in. But yeah, I like that, just setting it to 4. Cool. Yeah.
Is it okay if we input differently, or?
Yeah, there's a few different ways of drawing this, but as long as it operates correctly. Yeah, question.
Can we like output the reset into a box?
The reset into mux. So the reset is like implied right here. So there's just like a kind of implicit reset signal right here. That yeah, I would say we don't really want to ever kind of use this. This reset is just like fed into the flip-flop kind of by default. Is that what you're asking?
Because it says like you should pause it until the active low reset is activated.
Mm-hmm.
So I fed the reset low into a mux. When the mux is equal to 0, then I have to use it.
Yeah, great question. So what what the question was is, well, so if we need to make sure that it starts counting up again when reset goes active, then should we take this reset and like plug it into our mux? I actually don't think we need to do that because the reset should reset our counter back to 0. And so we can just assume that this flip-flop will reset back to 0 when this reset goes active. And then immediately after that, then we know on the next cycle, it will properly, it will start counting up again because now we're outputting 0 and then we're not equals to 4 here. So that means that now we're going to take this +1 path. So I don't think we need to actually touch our reset at all. And instead we can just assume that it just goes directly into our flip-flop. Yeah, question.
If we were to use an accumulator for this circuit, since an accumulator has a flip-flop within it,
Yeah.
can we assume that it would just take the reset signal?
Yeah, so if you wanted to do it with an accumulator, then usually we would just like keep adding 1, keep adding 1, keep adding 1, until when would we not want to add 1?
When it's 4.
Sure, yeah, when it's equal to 4. So yeah, you could just have a mux or something, or you could probably plug the like equals 4 thing into the accumulator, maybe with a NOT gate or something. Yeah, sure, yep, yeah, question.
We're not using the box just equal to 4 and then not into the header.
Say it again?
Like, so when it adds up like equal to 4 and then you go back to the header with a not sign of the not gate.
Oh, right, exactly. Yes. So yeah, another solution is you could just take this equals 4 thing and just plug it into this part with a NOT gate. That's what you're saying? All right. Yeah, I think we could do that as well. Yeah, a few different solutions. Yeah, question.
For the reset takeaway, for like all the buckets, for the
Exactly. Yeah. So let's quickly look at the waveform. So I'm going to shrink this down. So starting out, so Q. Actually, okay. First thing. So right here, do we know what Q is? We don't know what Q is. So actually, for both of these, this is just going to be unknown. We actually don't know. I won't grade this first little bit, but then immediately we see that this reset goes activated. So now we know that on the next cycle that it's going to be 0. So this is 0, and then it'll pass through, and so then D should equal 1, and then on the next cycle, then it will propagate through, and then now D now equals 2, and it'll propagate through, and now it's 2, and then all the way, then finally it will at some point start equaling 4. Let's just say it equals 4 right here, okay? But then we receive this reset. So if we receive this reset here, we have to be careful about it because we don't actually reset to 0 right here. We actually have to wait a full another cycle after that. Because if we reset right here, I mean, like, yeah, look, so our reset only became active like exactly on this point. So therefore, like, it didn't know about the previous cycle because it like samples kind of from the previous cycle. So on the previous cycle, it looks like reset was not activated. So actually, we will not have a reset there. But then right here, then now if we look at the previous cycle, see what we were sampling. Now it is 0. So now on this cycle now it will be reset to 0, and then D will go back up to 1. Yeah, be careful of the resets and the idea that it actually has to like be sampling what the reset was on the previous cycle. Yeah, question.
So where is D and where is Q on the diagram?
D is right here, and Q is right here. All right. Good luck on your midterm, everyone. I will see you on Wednesday.